go back and edit that class and make changes to it. But it's important because there are certain lessons that you're supposed to get in 530. One of them is it's a big project, an all semester long project. 2 is working in teams, and 3 is the maintenance aspect of it, going back to something you finished and changing it. Something like 90% of software costs are maintenance. So you had to change the file parser because the labels contain different standards. So you might tell the application programmer that's writing the code, okay, here are the rules for your labels. However, the rules are different for system code. So, for instance, you have labels like .init 13, and you have some with underscores in them. These are to avoid clashes. So in the case of the init 13 one, for instance, there's a group of constants in that IOMax file. And the problem is you can't have clashes. They're not part of macros, they're constants. If the author of this had used different conventions, it's possible there would be name clashes. So this was chosen deliberately as it's out of what's allowed for programming, for application programs. So this was chosen specifically knowing that there wouldn't be name clashes. But your macro processor has to handle those things. So you have to go back and relax the rules on labels for the file parser. All right, are there questions from any of you guys? I know it's due today, but if some of you are still working on it and you have questions, please ask. No questions. Yes?
For future assignments, can we get everything that it's going to need to have and take care of spelled out in the actual website? Because apparently there's a lot of stuff that we only talked about in class that's not spelled out on the website.
That's true. That's true. Part of that's on purpose. A lot of people have been cutting class, and this is a concern to me, so I've given important information in class only. That's part of the reason. The last part of it is the expansion, which means you're just substituting the parameters. So it's very easy to put the complete specs in there. I specifically mentioned that you had to be able to handle things like this and the parameter things. You know, you don't want to, I mean, you had to be able to work with those. I did not mention specifically in the assignment itself the dots, underscores, and numbers in labels. That's true, but we talked about them in class. So, okay, are there any other questions for you guys? I mean, making this happen is as simple as commenting something out, isn't it? I think so. All right. So then we will shift gears and start talking about linkers and loaders today. So the 3 processes here. Loading. And this is placing the object code into memory for execution of the program. The second part of this is relocation. And this is modifying arbitrary starting address. And the last piece of this is linking. And this combines one or more pieces of object code and provides the information necessary for references between them. So loading is pulling the program into memory so you can run it. So what is the process that has to happen here? Well, you obviously are going to read it from a disk, load it in memory. So how does the program start? How do you actually launch the thing? What's the mechanism? You got this object code, you copied it into memory, but that doesn't make the program run. What's the mechanism for actually launching the program? Nobody. Okay, tell me about the execution cycle. What is that? The execution cycle. This is the execution cycle. Continues infinite, as long as the computer's up and running. So for or while true, while one, different ways you can do it. Fetch an instruction from memory. Well, how do you know where to fetch it from? How does the computer know where to fetch an instruction? That's a great point. Well, there's this thing in the CPU called the program counter. The program counter always has the address of the next instruction to execute. So when you fetch an instruction, you go to or fetch memory at the address of the program counter. Whatever the address of the program counter is, you fetch that. You can go to execute, you store the result. Increment the PC to the next instruction. So this is the execution cycle. Here, when we load a program into memory, we put it in memory. And the last step, the easy step, is you place the starting address of the program in the program counter. That. Then on the next pass of the execution cycle, it fetches the first instruction in the new program recently loaded into memory and executes. Relocation. Well, back in the early days of computers, this was really not considered. There were single-user systems back then. I understand multi-user systems. And so there was an area of memory for application programs, and everybody used it, and they would go one at a time. I remember years ago going to the computer center and turning in a stack of punch cards. And there's a card reader, and it would read your cards through, compile and run your program, and give you the printout. They'd always go one at a time, and you couldn't have more than one user. So the first PCs used DOS, a disk operating system. It's a single user system. So the area of memory for application programs was fixed and known, and there was no competition for that space as one program would run at a time. However, when we start getting multi-user systems, that all changed. So if we hard code an address in a program, what are the chances we could actually have that address on a machine like Edoras? The answer is forget about it. Right? So how many people might be using Edoras at any one time? That's hundreds of people. We can't all have the same address. Can't be done. So what we have to do then is have relocatable code. What happens then is we set the starting address to 0, which is a signal that the program is relocated. So we set the address to 0, and then the assembler will go ahead and assemble all of the instructions. But they will be relative to 0. Well, of course, the program's not going to run at 0. So what kind of things need to be relocated? What needs modification? What can't run just as what we're going to relocate code. What has to be different?
Type of work.
Okay. Format 4 instructions, but not all of them. Some of them don't need relocating. So suppose I have this. Is that a legal instruction? Yes, it's legal. It's an immediate value, so you have the actual number 50,000. Would that fit with format 3? No, it won't fit. It's too big. So we have the plus for format 4 and the 50,000. So, do we have to do anything with that to load it in a different location? Not really. What's got to change? Nothing. So in the more general sense, what does have to change?
Or you can label it.
Not necessarily. Labels are okay. What has to change? Address. I heard the magic word. Thank you, Kenny. Addresses, where you have a memory reference. So, okay, if we have plus LDA alpha, that's a format 4 instruction, which means we have encoded the actual address of alpha. Okay, if we have the actual address of alpha, what are the chances that it's going to be right when the program actually runs? The answer is the chances are 0. If we start at address 0 for the first line of code, then alpha will be the number of bytes forward from 0 from the start of the program. Okay, so memory references have to change. How big a burden is this? With the architecture we are studying in this class, not so bad. The 68K architecture that you all have been battling with your recent project, the way all memory addresses are encoded is actual addresses, full 32-bit addresses, which means that every memory reference will have to be relocated. Also, remember when we started, we talked briefly about this SIC architecture. Well, we've been doing the SIC XE, which is the extended version. But with the original, you actually encoded the 15-bit address for all instructions. So then, what that would mean is that virtually every instruction would have to be changed. So what's the process that happens here with this? How do we change these memory references where they have to? What is the process?
Find displacement from the beginning, always increase it, then
Right. So there are a couple of ways this can be handled. We've started at 0. So if alpha has an address, let's just make something up, 1C. What does that 1C mean? That's the distance from the start of the program to where alpha is. So now when you load the program, you ask the operating system where it can go. And the operating system comes back and says, okay, you can load this at address 06114, let's just say. Okay, well then the actual address of alpha is the sum. That's where alpha will actually be located when the program is running. The next time it runs, it might be at a different place, but that will be where it is now. Which means the loading address, the start of the program, the address of where it's loaded, plus the address of alpha gives you its actual location. That makes sense, doesn't it? All right. So what we want to do is have some way of helping the linker, the loader, know what has to be modified. So we have to do modification of records, which is a listing of all of the addresses that will have to be modified. All right, so let's finish this piece. Another issue, or another way to handle this situation is with chips, with hardware. So the way the Motorola architecture works is if you ask for a memory location, i.e. you ask for this, then there's a piece of hardware in the machine that has the actual loading address, and it translates or changes it at runtime for each requested memory. So you ask for 1C, you get back what would be located at 1C if you started at 0, but in fact it's located at a completely different location. So that is called a memory management unit chip. And it would have the load address in it, and it would add on the fly. Okay, so not the best way to do things, but sometimes you have no choice. Then we have linking. Linking involves more than one piece of code. You have multiple pieces of object code. And somehow you need to establish relationships between them so that they can work seamlessly and you don't know where any of those pieces may actually end up getting loaded. So the linkers and loaders are typically a single program because can you load it when you need to make changes to allow relocation? Well, if you do, then you have to go back through and do this other step. So it's easier to have it as a linker loader as opposed to separate programs that run. So what's involved in linking? So consider the program you just wrote. How many pieces are there? I mean, that you can identify. You have the file parser. You have a macro preprocessor. What else?
Exceptions.
You've got your exceptions. Did anybody use a string? Yes. Did you write a string class? Oh, heavens no. So you want to just use it. Okay. Maps, vectors. So how many pieces do you suppose? And when you say vector V, the compiler has to be able to find the code for that thing. So we have multiple pieces here. And there has to be a way or a mechanism by which the different pieces of code can be related so that you can call vector V and it's found and executed. Questions so far? Okay. So dealing first with loaders. There is such a thing as an absolute loader. What distinguishes an absolute loader is the fact that there's no relocation possible or needed. So for some simple systems, there is no need for any relocation or linking. And so you would have what's called an absolute loader. So can someone think of a situation where no relocation would be required, no linkage would be required,
Just running one program.
if it's just running one program? So bootloaders are an example of an absolute loader, but beyond that, embedded systems. You have, let's say, a digital thermostat to run the heating and cooling in your house. Are you going to load a JVM in that thing? No, I don't think so. You're going to have only one program running in that. And so there's no reason to have anything